In the days that followed 3I Atlas's close pass by the red planet, the most forceful signal to emerge from our solar system arrived not as light, radio waves, or any electromagnetic trace, but as something infinitely more human. It came in the form of a report, published in China, yet felt across the entire scientific world, that didn't read like routine research. It read like a pronouncement. Every official line carried a weight that made skepticism feel almost juvenile, as though disbelief itself had finally overstayed its welcome. Nothing about the object, its orbit, its composition, its blistering speed had changed in those days. But somehow everything had. In the uneasy pauses between the report's sentences, in the carefully restrained expressions of astronomers who spoke as though language itself might crumble under what they were trying to convey, you could sense the shift. If confirmation has a sound, a texture, an atmosphere, then it felt as though 3I Atlas had been waiting for us to develop the courage to hear it. The story began on July 1st, 2025, when Chile's branch of the Survey Telescope Network's Asteroid Terrestrial Impact Last Alert System, ATLAS, registered an unfamiliar object moving rapidly across the sky. The detection wasn't unusual at first. Telescopes catch faint moving specks every night. But this object, once plotted and replotted against background stars, didn't fit any known orbital family. Its trajectory pulled outward, not inward, and the curve of its path placed it firmly beyond the sun's gravitational leash. Its eccentricity was greater than 1, its speed extraordinary, its incoming vector unmistakably foreign. When the Minor Planet Center officially designated it 3I Atlas, it joined an elite and unsettlingly small category. Interstellar visitors, following only 1I/Oumuamua and 2I/Borisov. These are bodies that cut through our solar system on one-way trips, their origins in the distant dark, their journeys spanning millions of years. Their fleeting presence is a reminder of the vast cosmic traffic that occasionally brushes against our small domain of light. Astronomers across the globe scrambled to observe it, allocating precious telescope hours, measuring its brightness, analyzing its coma, and capturing spectra before the object slipped too deep into the glare of the sun. Its heliocentric velocity exceeded 200,000 kilometers per hour, fast enough that each hour without observation erased possibilities, widened models, and deepened uncertainties. The urgency was palpable. And then, in late September, during the 36 hours when the comet was most active and most critical to observe, the Western world's major telescopes went dark. None of the shutdowns were suspicious in isolation. The Hubble Space Telescope underwent a scheduled gyroscope recalibration. The James Webb Space Telescope initiated an instrument shift requiring thermal stabilization. The Very Large Telescope in Chile paused operations for essential mirror cleaning. Gemini North and Gemini South both entered planned downtime. Each event made sense on its own schedule, yet the eerie simultaneity of them created a global observational blind spot. As 3I Atlas moved into the sun's glare, its moment of maximal outgassing, its most revealing phase, nearly every Western eye in the sky blinked at the same time. During the blackout, 3I Atlas underwent dramatic transformation. Its coma, the glowing cloud that forms when a comet's ices sublimate into gas, expanded rapidly. The tail stretched under solar radiation pressure, lengthening with every hour. Observations prior to the blackout suggested the nucleus could be as large as 5 kilometers or as small as a few hundred meters. The uncertainty came from the object's unusual brightness. Something about it refused to behave like common comets from our own system. Even more intriguing were the spectral signatures recorded by JWST and NASA's SPHERE-X mission. Instead of water vapor dominating its coma, carbon dioxide did. This anomaly hinted at a birthplace far colder than the outskirts of our Kuiper belt, perhaps the deep freeze around another star, or a region shaped by thermal processes entirely different from those that shape our own comets. But while Western observatories dimmed, a cluster of high-altitude telescopes in Tibet, Qinghai, and Yunnan continued operating unimpeded. Their schedules did not overlap with Western maintenance cycles. Their night skies were clear. Their instruments, perched thousands of meters above sea level in low humidity and thin atmosphere, remained trained on the rapidly evolving interstellar visitor. In the silence left by the West's absence, China's observatories captured everything. The Chinese network recorded the comet's rising luminosity, mapped subtle shifts in its color, and tracked the expansion of its coma and tail in precise detail. These telescopes, with mirrors ranging from 1 to 2.5 meters, fed light into cooled CCD sensors that time-stamped each exposure with millisecond accuracy. Such precision was essential. When an object moves hundreds of thousands of kilometers per day, even tiny timing errors can warp its projected path. Each image, preserved in FITS format with complete metadata, coordinates, filters, exposure, temperature, sky conditions, was transmitted to processing centers in Nanjing and Beijing, where petabyte-scale clusters calibrated, verified, and store the data. By the time Western observatories returned to operation, 3I Atlas was already more than 1.2 million kilometers from its previously recorded position. Without the uninterrupted Chinese observations, reacquiring it could have taken many hours, and crucial information about its behavior in sunlight would have been permanently lost. Instead, thanks to those mountain stations, the object's coordinates were known within a few arcseconds. Western telescopes could point confidently the moment they reopened their shutters. The data gathered during those 36 hours offered a level of resolution and continuity that might otherwise have been impossible. Continuous sequences of multi-filter exposures revealed that the comet's brightness increased by about 0.3 magnitudes, possibly indicating a brief jetting event on its nucleus. Measurements of the tail's color and morphology suggested the presence of unusually large, carbon-rich dust grains. Yet another feature uncharacteristic of typical solar system comets, but consistent with materials forged under different stellar conditions. As the Chinese data flowed into international databases and the Minor Planet Center incorporated the updated coordinates, the orbital model of 3I Atlas sharpened dramatically. Positional uncertainty shrank from roughly 25 arcseconds to under 5. Within hours, teams worldwide had access to early preview images through China's virtual observatory portal, which had quietly become the sole active source of fresh observations during the blackout. The contrast between the vast infrastructure of global astronomy and the fragile dependency created by downtime was suddenly impossible to ignore. But collecting images was only the beginning. Verifying them was equally essential. Calibration, cross-referencing, and alignment with global standards transformed raw data into reliable scientific truth. China's teams used Landau photometric sequences for brightness anchoring, harmonized them with the Sloan Digital Sky Survey's magnitude system, and ensured that wavelength calibrations were done with thorium-argon and neon lamps to maintain sub-angstrom accuracy. Astrometric solutions relied on the Gaia DR3 catalog, bringing positional precision down to fractions of an arcsecond. Independent verification teams in Hong Kong and Taiwan tested the results, and every measurement fell within expected uncertainty ranges. The data not only held up, they reinforced one another. This meticulous work ultimately confirmed what early orbital FITS had implied. 3I Atlas was on a hyperbolic path with an eccentricity around 1.19. It was not merely a comet with an odd trajectory. It was not a misclassified long-period object. It was undeniably interstellar. Its materials, its behavior near the sun, its unique spectral composition, all pointed to an origin well outside the boundary of our solar family. Beyond the science itself emerged a broader, more human story about power, coordination, and the limits of even our most advanced machines. Astronomy often celebrates aperture, the wide, gleaming mirrors of the world's great observatories. These instruments dominate images of scientific achievement, towering symbols of humanity's attempt to reach farther, see deeper. But aperture is only one form of power. The 36-hour blackout showed that flexibility, distributed observation, and automated vigilance can be just as decisive. China's